Hello, we are ECE Group 17, and this is the final video presentation of the Smart Balloon Detection System project. First, I will give a brief overview of the presentation ahead. We will start with an introduction and background of the project, followed by an exploration of our proposed solution and the progress we made on it. Project details such as the timeline and budget will be discussed at the end. There exists a need to enhance security at indoor areas and events with emerging technology. Such venues would benefit greatly from non-stationary image capture and patrolling. Identifying individuals present at a given event would also have added benefits. The overall idea of the Smart Balloon Detection System is to design and produce an aerial surveillance system capable of sustained flight, navigation, image capture, and image processing. It's intended for picture taking at indoor events, such as sport games, presentations, concerts, etc., to provide security monitoring capabilities. Advanced functionality such as self-navigation, object detection, and facial recognition will be integrated as well. To make this design possible, the following main components are required: a microcomputer to control the system. The design would benefit from a device that is easily compatible with various camera options, has built-in Wi-Fi communication, capable of transferring image data and movement signals. It's expandable so can accommodate possible changes or upgrades, and also takes advantage of existing standards. A helium balloon to carry and be the base of the design. The balloon should have controllable movement that can then be modified to be automated, and have a relatively high weight capacity to carry all of our components. A simple camera capable of capturing consecutive frames. A relatively basic camera is desired because of its low power requirements, but also needs to be able to capture high enough resolution images for reliable image processing. Some kind of object detection technique, something like an open source detection algorithm such as neural networks would work well. And finally, a power supply to feed the whole system. A small rechargeable lithium-ion battery would work well because it has the output of required 5 volts, it's lightweight, and provides enough to sustain the system during testing. Now that we know what the Smart Balloon Detection System will be comprised of, it's useful to look into similar existing ideas. Our design is not reinventing the wheel, so there are a couple of solutions that meet some of our design requirements, but none with all of the compatibilities of the Smart Balloon Detection System. Here there are 4 products that share concepts with the team's planned design. None of the helium balloon designs are made commercially. They're more so just projects by big tech companies. They also do not have all the same capabilities. For example, they are manually controlled and do not include detection software. Drones have many of the same requirements that our system has, but they have moving parts and are quite power hungry, both of which our design aims to eliminate. To give a better understanding of the project, I will briefly explain some of the relevant theory in the design. One of the most important balancing acts of the project is weight capacity. Since we are relying on the buoyancy of helium as our source of lift, we cannot encumber the balloon with too many components. This reduces the options of the design, since heavier components will typically add more functionality. The image processing will primarily be object detection, utilizing algorithms such as machine learning and neural networks. The wireless communication would need to be capable of decent range and working beyond line of sight, which eliminates technologies like IR. Also, it would need to be fast enough to transfer data for real-time analysis. Finally, it is necessary to define automated movement in the scope of this design. The design will be automated to the degree of navigating and performing surveillance without human involvement, but has the option for manual override controls.
This is the proposed prototype designed for the Smart Balloon Detection System. The system is designed to perform real-time object recognition and facial recognition, also with certain level of automated navigation for patrolling. It is composed of the flight system Raspberry Pi 4 with camera and a remote computer. The flight system is an existing product made of a helium foil balloon and has a remote control that uses the infrared communication to navigate the balloon. The Raspberry Pi 4 was chosen because it has an integrated Wi-Fi and extra port for future expansion. This slide demonstrated the operation details. The images captured by the camera would be transmitted to a remote computer via Wi-Fi on the Raspberry Pi. Then object recognition using the techniques of You Look Only Once, or YOLO, can be performed real-time. YOLO is an open-source software and operates by applying a single neural network to an entire image. Then divide the image into regions to predict bounding boxes around objects and the probability of detection. The control signal could be sent from the remote computer to the Raspberry Pi 4 for navigation. The movement of smart balloon detection system is controlled by flipping the fins for XY movement and moving the weight on the rail to change the altitude. The control logic is implemented as so. The detection keeps searching for people. If none are detected, the balloon moves a little bit. When people are found, the facial recognition would be performed based on the original design. Before the COVID-19 shutdown, the team made the balloon fly, found a way to stream the video data captured by the camera and successfully make it available to the remote computer. For movement, the fins and weight on the rail can be controlled via the Raspberry Pi. In addition to that, we have tested the object recognition with YOLO algorithm and have a high accuracy.
The smart balloon detection system has a lot of impacts regarding economic, environmental, social, and ethical. The smart balloon detection system is designed with an inexpensive camera and a processor that have a very low energy requirements, which provides an economical choice for the customers. Without any harmful fans and taking advantage of buoyancy of helium, the product is not only an environmentally friendly solution, but also a safer option which reduces the potential ethical concerns. The decorated balloon increases the entertainment to the guest and makes security monitoring feel less intrusive and intimidating, which brings a positive social impact. The design utilizes pre-made components that already met electronic and safety standards. Since the device is designed to be operated indoors, there are no flight regulations that must be met. The following IEEE codes were priority in the design phase to ensure a safe design. IEEE Code of Ethics 7.8.1 is about public safety, and 7.8.5 is about societal implication of emerging technologies.
Over the terms, the team has made significant progress on the project, but before talking about what we have made, let me briefly give an overview to help imagine it. Our project is designed for indoor events. The flight system will navigate automatically and carry a camera that captures pictures and videos. The images will be sent to a cloud or local computer for image processing. Its goal is to identify people through object detection and trigger alarm accordingly. By the time we stopped live testing, we have accomplished the following task. The air swimmer has its own remote controller. We disassembled and reconfigured it with a Raspberry Pi to remotely control movement by programs on the PC. The picture and video has been successfully captured by the camera and transformed to a PC. Then, using YOLO to perform object detection on the video feed allows the real-time monitoring. Like mentioned in the solution slide before, the team did not complete all planned parts of the project. One of the main issues is Each part was worked on independently before the changes to the class, so integrating all the parts became impossible while staying physically separated. At the end of the prototyping, the team is able to use our Raspberry Pi to control the flight system, but it exceeds the weight capacity of the balloon. Solutions to improve this, such as adding smaller balloons or using small fans, were also being researched. The Raspberry Pi and the camera can capture video frames that can be transformed to a computer. YOLO can only be performed on the local computer's camera feed, but not image captured from the Raspberry Pi and camera. Here is our little demo of YOLO. Like you can see, there are different classes such as person, chair. The percentage is possibility belonging that class.
Originally, the goal of the design was to use 3D image processing techniques to accomplish self-navigation and facial recognition. However, after discussion with our advisor, we changed the automation goal of the project from self-navigation to a manually controlled system. Since the object detection software tool, YOLO, was introduced to our team, we studied and modified YOLO to perform object detection. This changed the image processing goal from 3D taps images to 2D image processing. Then the team was focusing on downsampling the video frame rate to reduce data transmission and make image processing easier. Due to YOLO's own limitation, the object identification scope had changed from facial recognition with depth images and thermal detection to pattern recognition and object identification. A large helium balloon was planned to be used during the final stage to carry the whole system in the air while floating freely. However, the coronavirus pandemic forced project testing to stop before integration of all the individual parts to a whole system. Because of this, the team changed the final system function expectations of the project from a single integrated system to each individual part successfully working independently.
This is our project timeline through all 3 turns of the project. As you can see, different colors represent different classes of content. Blue is research and concept development, which the team spent most time on during the first turn. The red is system design. We have designed or changed the project scope at the beginning of each turn in order to make the design more feasible. One of the most important parts is documentation, shown in orange. This includes weekly report, progress reports, term final written reports, and oral presentation. Green represents lab and other testing. Note there is no testing occurring in the last turn. And finally, the purple parts are other information. So here is team member responsibility. There are previous and current 2 sections. Previous is before this spring turn. So Evan and Wan Yu are the designer and the tester. They are responsible for the technical parts of the project. Yumeng is the recorder. She is responsible for record, keeping the updating and the weekly report and the data analyzed. John is the team leader. He is responsible for communication between faculty, arranging weekly meetings, and making plans for the project. So for the current situation, Yumeng is working on the blog, social media posts, and documentation deliverables. Wang Yu and John are working on weekly meeting record and documentation deliverables. Even design and test the data transmission, Raspberry Pi related issues. Due to the virus, the expense of the project was stopped at the end of the winter term. Since there were no actual costs during the spring term, the total budget for the project is about $150. An additional air swimmer and a helium refuel are funded by Dr. Du's department.
Thanks for watching our presentation, and feel free to contact us with any questions that you might have.